Okay, so this video is going to address how you do part two of the assignment four. So in the part two of the assignment four is your challenge is to take a program like bigint and convert that to assembly code and make it more efficient to run faster and faster. So here's how the bigint looks like. It does have functions like bigint larger, which takes two arguments and one local variables. And then if you go into the bigint add function, which takes three arguments and four local variables. And then they have loops, conditional statements, and so on. So the challenge here is to convert this into uh, an assembly code. So what I'm going to do is to show you an example where hopefully you'll be able to get some ideas about how to convert this program into the assembly. And in order to show you a few things, what I did was I wanted to show you a demo where some of these ideas are there, but in a different way. So let's suppose that I have this file called struct.h. So here I have a struct which has a length and some kind of a pointer to a long. This will actually become an array. And then you have a max. So what I'm trying to do here is that I will have an array of some long things, which is of this length, and then I'll try to find the maximum of that. So I have a type definition, which is similar to the bigint. I have a big S, which is a pointer to one of these structures. And then find max will take two long integers and find the max and return long, which is similar to the big thing, the larger that you have to find here. And then you have a set max, which is more like bigint add, but I'm doing something else here, which is like setting the maximum of the array to this variable here. So what we're going to learn here is then how to do that. Hopefully you can take those ideas and apply to this file here. So let's take a look at the other files. Like for example, I have struct.c, which is this. And so I'm going to equate this file to this. I don't have all the bells and whistles here, but it just gives you an idea. I have bigint larger, I have find max. So you'll see how I convert this. You have bigint add, I have this, and they all have reference variables, local variables, and so on, and loops and other things. So my goal is to really do this. When I do this, I'm going to convert this to assembly and then run this program. So right now I can run this program by doing the following. I say struct.h and struct.c, and then I have struct demo.c. And then when I run this program, I'm just doing something nonsense that doesn't make a lot of sense. What I'm going to do is to give a number, and it's going to create an array with 0 to 199, and it's going to find the max of that array. So just creating an array of a different size and give you the max. So let's not worry too much about the details, because what we are really hoping is we will learn how to convert struct.c. Hopefully we can apply those same lessons to these two functions here. So we'll take a look at that next, how to. All right, so the first thing that's recommended for you to approach this assignment is to convert your bigint add function, which is given to you, to a form which is flattened. So in this case, in my example, this is just a demo to help you out. I converted the bigint, the struct dot C without loops. So, and then I can run it by doing this. I will compile the struct flatten.c with the struct demo, and then just run it, and convince yourself that you get the same output. That's really important as the one that's not flattened. So that's where you start first. Before you move forward to the assembly, you must. So now comes the sort of the hard part where we have to convert the bigint add.c into bigint add.s. As we discussed before, you must create the flattened C code and test it, and then you can convert the flattened C code into x86. And let's take a look at the process here a little bit. So there are a few things that you need to understand here. First of all, the memory map. So for example, how the memory is organized. So in my example, I took a structure which has length and max and an array with the max size of that. And then this is how I would think about this stack frame when I create one of these stack frames where you have um, the obig and the objects. Like for example, in this case, we will send the obig into the stack, and then index, and then ulmax and ulmax. So this is how it's going to look like when you call the function setMax. So your stack point is going to be here. 8 from that would be ulmax, and so on. So you can assume that for 24 from there is the obig. So whatever the content you have here would be what you need to get. Like for example, obig would be equal to 24, the value of obig, or what's in the obig. The address of obig would be RSV plus 24, but the content of obig is going to be 24, which is the displacement from the RSP. And then you look at the content memory location, and maybe as an example, you see 1000. Now, if you dereference 1000, that means that you go to the memory and see what's in the 1000. It's in the heap, because this structure comes from the heap. So if you look at the content of 1000, you're going to see a length. The content of 8 away from 1000, you'll see UL max. Content from 16 away from 1000, you're going to see a list. Now, if you look at a list of 2, then what you have to do is you take the displacement of the field, which is 16 from the beginning, and 1000 is essentially the address or the content of this place here, which is in some register here. And then you can take 2 times 8, which is along. So this is really what you need to think about. So you must have this in a register, which is usually some displacement. RSP would give you that number, which is what you wanted. That's the content of the obig. Again, obig is at RSP plus 24. Then we want to get the content, and from there we can find the rest of it. Okay, so that's how we are going to think about that, and we'll go from there. Okay, so before we start looking at the actual code, I want to emphasize one more time the importance of understanding the structure, the stack frame. So when you create a stack frame for setMax, you would have 4 variables. Obig would be the farthest away from it. That's 24 from the RSP. And the last one, UMax would be for the first one. So once we have obig, which is 24 from RSP, we can dereference that and find the content that takes you to an address, say 1000. And then if you dereference that, then you can get the L length and so on. Now the key here is that putting this thing into a register and then start looking through how to get to the next location and so on. So essentially, if you can put 1000 in a register, that's all good, right? So let's take a look at the translation of the code. So here's the flattened C code, and so here's the actual assembly code. So the key thing here is that let's start from find max. So we have a find max. It's very important to say global find max. And then we have 3 variables. L first would be 16 away from the top of the stack frame. This stack is going to have 3 longs, so it's 24 bytes. Stack byte count is 24. Lmax is the last thing to go, so that would be 0 away from the RSP and so on. L second is the second one away from RSP and so on. So having these symbolic names make it easier to write code to translate this code directly into the assembly code. So the way we think about that is we have 2 arguments coming in, RDI, RSI. Those are the first and second. We push them into the stack. We save the space for Lmax, so that's all good. Now we start comparing things. Now, Note that when we compare, it's very easy to write code. So if you want to get, say, L second, we take L second and we dereference the RSP, which would give you, for example, L second is 8 away from whatever the stack frame is. So we know where the L second is, and if you dereference that, you can get the content. So it's going to be a number in this case. Put that in RAX, compare L first RSP, which is the L, where the L first is in the memory. This is the memory location every time you have this parentheses. We compare it to RAX. Now, notice that we always compare in the compare operation. We look at the second operand compared to the first one. So it's greater than or equal to. So this means L second is greater than or equal to. We jump to that. So I think that should be good. And then the only thing I want you to think about is this one here. It's very important that you add the stack byte count to before you leave the function to the RSP. If you don't do that, it could crash. Your program can crash. So this is a very important thing to do. And let's take a look at the more challenging function, which is the setmax function. So this is given here. And if you look at the setmax function, again, I'm writing the code for that. Same thing, I'm going to use symbolic names, same as this. I'm going to use capital letters, so I don't have to worry about whether it's lowercase or uppercase. Notice the obig is the first thing to go. That's 24 from the top. And then the I index, UL max. So I index is like 16. UL max is like 8. And the top of the stack is the UL new max, which went the last. So by knowing these things, I will be able to refer to these memory locations easily. Now, what this gives you is sort of like the offset in your structure, which is kind of given here. This is the offset. L length is 0 from that. UL max is 8, and the array is from 16. So I think that offset is very important there. And so we have the offset for the stack, big stack. And then we also have the stack byte count. That's the how many bytes we allocate for the stack frame for this function when we call that function. Now the way we call that function is I'll go over a few things, but you can find this code on Salon if you're interested in looking at it to see how it works. We push the first one, RDI, so that's the address, into the stack, and then we reserve space for the other 3. They are not initialized. And then we have the loop. So let's take a look at the loop here. So begin loop. Now prior to that, we have I index 0. That's easy to do. So I index 0 is simple as saying, let's move 0 to I index RSP. That's the memory location where we reserve the I index. So remember, we have something reserved for I index here. So that's the memory location. And I index is you'll notice that the I index is going to be 16. So whatever that memory location, we're going to push the 0 into that. And then we do comparisons and then jump and so on. So this is one of the things you have to understand. First of all, you want to understand this part here. How do we get to that? Okay. So first of all, we have to get O big. So if you look at O big RSP, which gives you the memory location, what's the content in that location from the RSP, which is say 1000, right? So in this case, and if you look at the content at that point, so for example, if you look at what is the content here, which is 1000, if you look at the content of that content, which is parenthesis 1000, you're going to get I length. So that's what we're looking for, right? So in this case, we are saying, okay, let's look at the content of obig. That's what is the content. We know what the obig is. Obig is a reference, it's the address. And then we want to know what the content is. And if you look at the content of content, this gives you the obig length. So what you get is obig length, which is in RAX. And then I decrement by 1 RAX. So this means that I have in RAX this quantity. And then I compare RAX to I index here, which is a straightforward comparison. So I'm comparing to see that because they are both unsigned long, I'm using JAE. So I'm comparing to see if this one is bigger than or above or equal to RAX, which is in fact this quantity here. So it's the I index. I make it a habit that I always write the bigger one here to the right. That's the I index, and then I could use the JAE, something like that, right? So in this case now, let's take one more look at here. So this one says um, I have to call find max. So I have to get this here. So how do I get that here? So I want to get, say, that 1000. Okay, so that's going to be in RAX. That's the base address for the array, the stack frame, right? And then, so that would be like, if you look at that, that would be this 1000, okay? And then what we're going to do is we're going to say, let's get the I index, which is this one here. That's in R10. And then we have this really cool operation where we can look at the base plus R10, which is the index, times 8. That's how many bytes away from that. We also need the displacement A list. In this case, what we're saying is let's go here and let's go to this and let's go to 16 bytes from there. So that's what we are saying. So we want to somehow get to this, whatever the location reference by the array. So that's the key thing to understand, that this quantity here is obtained, put into RDI. That's what we do. We're going to put that into the first argument to the function. Now note the second thing. I'm going to get the I index and I'm going to increment I index. So I'm going to get I index plus 1. And then I do something really similar to send the second argument into RXI. And then I call the find max. And then once I get the results, which is in RAX, I'm going to move the result into UL new max, which is given by this. And the rest is quite simple and quite similar. The only thing you have to, again, be careful is that you must add the stack byte count. In this case, we have used 32 bytes, so you must add the stack byte count to make this work. So let's take a quick look at how this works. So when you're trying to convert it, compile and run it, so we will have, let's say, we can do this something like this. So I'm going to say gcc struct.c and struct.demo.c, and then I could run it for, actually I will try to find the time for 500,000 things. So notice that it's 0.014 seconds. That's what I need to get this thing. It's fairly very straightforward algorithm. So if you have, I'll go through some of the debugging questions. Now, obviously in this case, I'm assuming that you know how to convert it correctly. If you don't convert it correctly, then you'll have to use the GDB, which I will have another video. Now, key things to remember are how to access fields, how to compare things. Those are really important, and adding the stack byte count. Those are the things that's going to really be helpful. So be disciplined in this case. I try to be very disciplined. I try to use the base of the array to be RAX all the time, so I remember that. I try to use the R10 to be the index, so that helped me to think in a certain way. So I can think about base plus the index and the size of a long int and how far this A list is from the big structure that you have. So that's the key thing to note in this case. We'll take a look at the optimization. All right, so part 2E is about optimizing code. Now that code ran in whatever the seconds. The key thing in part 2E is that we're going to, so if you look at the code that I showed you in part A, so notice that I'm copying stuff into the stack, I'm pushing stuff into the stack. So this is all memory. I'm moving things back and forth between registers and so on. Now that can be very inefficient if you're doing this again and again and again. So one of the things we are suggesting that you do is that if the parameters come through the caller saver registers like RDI, RSI, and so on, just leave them there, but be careful. So essentially avoid using memory and reduce the number of instructions. So you could do both of those things by doing this. So I'm going to demo that. Once again, you'll be able to find my code in the in Salon, this demo code. So let's take a look at the difference between the regular struct.s, and then I'm going to show you my struct optimal.s. So hopefully you'll be able to follow the same thing. Now what I did was I made a copy of this and then I start changing it. The difference here is that instead of having a memory offset 0, I just use the symbolic name to name a register. So if I talk about Lmax, then I'm talking about RDX and so on. And then L2 is RSI. Notice that I know the arguments come to this through, this would be RDI. The first argument, this is second argument, so I'm going to just leave them there. I don't have to do anything there, right? The reason I'm pushing these three things is that if there was anything in those registers when they came, I must save them while I'm manipulating those registers, and then I must pop them in the opposite order of saving them, so that they're going to be restored when you leave this function. That's really important. Save a copy in the memory. So in this case, it's the memory. It's a one-time thing. And then pop them up in the opposite order so they can be restored. Now notice how much instructions that I'm able to remove. Like for example, this one here. This one statement here, it says if L first is less than L second. I need 3 instructions to do it and a lot of memory instructions. Now, in this case, I can just do this in 2 instructions because L first is in the RDI, L second is in RSI. So I said if L first, so obviously in this case, L second is the one compared to L first. So if it's greater than or equal to L first, I will go to the L statement. So I just have only one statement that replaces these 2 statements. So that's a great thing. Plus I don't do any memory reads and writes. And same thing, you will notice that in other places like Lmax equals L first. It used to be 2 statements. I had to write memory to a register, write the register to a memory. Instead of doing that, I'm just moving things around the registers, and I'm not worried about. I just need to return the final thing Lmax through RAX. That's the only thing. So if you look at this code and this code, I've reduced the amount of instructions, and I also reduced the, I pretty much don't have any memory accesses here. If you look at the other function, I've done the same thing. So in the other function, setMax, I did the same thing. So I use the RDI, which is the first register that comes through. There's only one comes through. And the RSI, RDX, RCX, I'm using it for the local variables. That's fine, as long as I'm consistent. I have all these offsets and other things. Now let's take a look at some of the code that may have improved. Like for example, if you look at the a piece of code like this code here, if L index end loop, right? So in that case, what I'm doing is, again, obig is going to be a register. It's RDI. So I'm moving stuff between registers. So this is a very efficient operation. I'm decreasing stuff from the register. And then I'm accessing some access to memory, but that's very minimal. That's very quick. And some access to memory here. So pretty much I'm doing using these registers. Again, I encourage you to take a look at this code on Salon so you can see you can compare the 2 codes side by side, how the optimal code and the struct.c code looks like. Now, what I like to do is to, again, notice that there are a few things that I don't have to do. Like, for example, I don't have to add the stack byte count. There's no need for that because I didn't use a stack at all. So these are all registers that I'm manipulating. Let's see how well this runs. Now, if you recall, the previous one ran in 0.014 seconds. So I'm going to try to use the optimal code here, see how much gain I can get. and then I'll run this with the same thing. Now notice I cut down almost a half, 0.14, 0.14 to 0.008. So notice without having the memory access, I can come down the time. So that's the part that this part here you're trying to optimize. The third part of the 2F part is the highly optimized. There are three things that you have to do. Um, One thing is to reorganize the loop. If you actually go to chapter 3, section 3.67 in the book or in the videos, here given under the you can find these things, like for example you can listen to a video on Salon, so you have a bunch of videos in here, and then inline, meaning that without having to call the function you can put that inside the code. In fact, this also will improve a lot your performance of your code. Inlining will improve somewhat, but your real improvements will come from by cleverly integrating the add CQ instruction. So this is the end of the